to Science Night. Please stand by.
Welcome back to Science Night, the Science Night podcast. We've relaunched, we've rebranded. It's a rebirth of sorts. You're used to hearing my voice, your friendly host James, but I've added some people to the fold, and I think that with the addition of these two co-hosts, the new look, the new sound, the new topics, you can't say we're not trying anymore. And that's really what we're shooting for with the relaunch of this podcast. So I am going to introduce the people who are standing by and waiting so patiently for me to stop talking, just like all of you. Let me introduce Chris Goulet and Jason Organ. Chris, why don't you tell us who you are and what you're going to be doing with us?
Hi there, my name is Christopher. I am not a scientist, but I am a podcaster. So I am going to podcast science news to scientists and non-scientists alike. And hopefully, even be understood. But we'll see.
Jason, why don't you tell the kids listening at home who you are and what you'll be doing with us?
Thanks, James. My name is Jason. I am not a podcaster, but I am a scientist. And so I hope to lend a little bit of support to the science side of the Science Night podcast. I'm excited to be on this journey with James and with Chris and with all of you. And so hopefully we can talk about some really interesting, cool stuff with the scientists who are doing that cool stuff and bring that to you. Their stories are phenomenal.
If you are a long-time listener to this podcast, you'll notice that there are some changes. We're going to start every episode off with a news segment. You're going to notice that there are shorter, more concise, and probably better segments contained in each one of these episodes. So we're looking more at like bite-sized science going forward, but it's still going to be really interesting people telling you about their story, their science, the work they do, and how they came to do that work in a fun way. So I think we're ready to start our very first news segment. I am going to let Chris take it away from here.
Jumping right in, we're going with artificial intelligence. Not your average run-of-the-mill 4-mile-long if statement that you may be used to. No, what this is an entirely new mapping of the known proteome universe, galaxy, dimension? I'm not really sure. This one took me a little while to understand, and so I'm going to do my best to relay what I have learned. In short, perhaps you might be familiar with the project Folding at Home, a program that you run on your computer which aims to help researchers predict how proteins are going to fold. Why is this important? Well, proteins, when you're trying to create a substance like a medicine or a therapy or a treatment for an organism, part of the process is you have to make something that isn't going to kill the target. And the way that you predict that before you actually stick something into an individual is by trying to guess and predict how the proteins are going to fold and thus have an effect on your body. It is very complex three-dimensional object that it's difficult for our brains to really wrap around how complex these structures can look, which is why it takes computers an awful lot of power and compute overhead to actually calculate these permutations of these three-dimensional objects. Until now, when you have this project called AlphaFold 2. Now, what AlphaFold 2 has done, which is so revolutionary, is it has run this model over and over and over again and concocted a mapping of the known proteome that gives a much higher degree of predictability as to the accuracy of these guesses these structure foldings than ever before. It's not to say that they have perfectly mapped how proteins are going to act forever and ever, amen. That's not really the cool thing here. But what they've done is created a system by which the most important and prevalent protein structures that you're going to find in living organisms are mapped with a much, much higher degree of certainty as to their accuracy than ever before. And that's really cool, because what that means is going forward, it's going to make it much easier and faster for researchers to go through this process when they're trying to create a new drug or therapy. And it's going to make the development process for these new techniques and products much, much faster and much, much better. So that's pretty exciting. And I thought this was a good place to start, considering we've been living through a pretty wild time for, understanding viruses, and especially the process of bringing a vaccine to the table under these, times of COVID that we live. What do you guys think?
It's a great point, Chris. You were talking about, proteins folding and why we need to understand that, but we didn't really talk about why that's important to know. We talked about the fact that it's important to know. And so I think we should sort of revisit that for a second. So, when a protein is encoded by our DNA and it's made, right, our DNA is transcribed into messenger RNA and then translated into a protein. Knowing how the different parts of that protein, the different amino acids that are in that protein, are going to interact with one another, and whether they're going to, want to clump together or they're going to repel each other, that's going to sort of allow us to sort of make a prediction about how, when I say us, I don't mean me at all, but science, a prediction about how that protein is going to fold. And knowing how that folds, as you alluded to, Chris, is important because, the different parts of a protein are going to interact with different molecules in our body. And sometimes they're going to fit into the hole, and sometimes they're not going to fit into the hole. And so those interactions are important to understand. So, rather than kill us, we want to know how proteins are going to fold. So we've been talking a lot about proteins lately because of the spike protein with regard to COVID. And it's something that maybe people haven't thought a whole lot about in the past. And so you were making a really nice connection here to the fact that, we have these new vaccines that are made on messenger RNA technology. They're not actually putting any DNA into our bodies. They're putting RNA into our bodies, which again is the transcription of the DNA. So one of the common talking points among individuals who are vaccine hesitant is that they're nervous that DNA inserted into their genome might become, deleterious to them, might really make them suffer, right? And the simple answer to that is, well, there's no DNA in these vaccines at all. It's RNA, and it can't insert itself into your genetic code the way a DNA-based virus would. And so this cool AI technology predicting how different genes that we know are in the human genome, but we don't know what the protein looks like. We know the sequence of the amino acids, but we don't know what that protein necessarily looks like. That's what this cool AI technology is allowing us to make these predictions now. That's the really cool stuff about this new series of papers that are out.
And I didn't understand this, at first. It took me a couple reads to get that it's again, it's not, they've suddenly got these models that illustrate a perfect structure of every protein possibility that could exist. It's not really like they've mapped it out in the way that we understand the mapping of the human genome. What it is being able to predict within a spread of accuracy depending on the input that is given, right? That's really the thing, is it's it kind of shortens the distance between those 2 points.
Absolutely. That's what's exciting about it. There's finally computing power that will allow us to do that, and it's machine learning, right? It's artificial intelligence. It's self-learning here, and it's going to help narrow that gap.
The thing that I really loved in reading this was what came at the very end of the paper, which is the source code for everything they did. This is as open sourced as you can do in science. They've given you everything. And I think going forward, if we want to talk about demystifying science, just have it be out there and available for people to see is a good thing. I work with a lot of biological anthropologists, and that is a touchy subject in that field specifically, but I think in a lot of different scientific fields, the idea of having this information available for everyone in some form, obviously I'm not saying that every fossil should be out there for everyone to hold, but there's things like MorphoSource where you can upload the 3D print file so that everyone can have a plastic version of that in their hand. It's really important to share the information. Sometimes we get a little bit too protective of the science and forget about the sharing and the communication side of things.
It's something that we noticed works really well in the computing space when we had problems that vertical compute power could not solve. We couldn't just throw more and more horsepower at a single node of computation. What we decided to do was distribute it and make computers work together in these giant networks, and we call them clusters. And, what do? They have to share context and information across each other for the collective computational power that exceeds any one node's possibility. And it turns out you can do the same thing with humans, but unlike computers, humans start to want things and have opinions. And so there's, there's some other issues that go along with it that are maybe more in the realm of passion, but it really has shown to be a model throughout history that works in terms of pooling our resources and extending the power with which we can reach.
You make a really good point here, Chris, about the power of teamwork, right? And the reason I'm bringing this up is that there's been a movement over the last, I'd say 10 to 15 years, especially with regard to federal funding for science in the US, to really reward team-based science, where you have multiple laboratories working together to solve a problem from many different angles, rather than funding a research program in a single lab. And now we're at sort of the next step. So, everyone's moved in this direction of team science, or a lot of people, the most successful approaches are team-based science approaches. Now we're moving to an open science domain where people are publishing source codes and asking for input, right? And putting things up in preprint servers, which actually is something we want to talk about a little bit later. And sharing information before it has made its way entirely through the system, because that early feedback is really important for making the next set of decisions. So it's an interesting time for science. It's also a terrifying time for science communication because of that. And so, the general public is not used to seeing science happen in real time. They're used to seeing an end result of a series of experiments. They're not used to seeing that experiment happening while they're waiting for the data. Scientists are used to seeing that, which is why failure happens all the time, right? I mean, why we're okay with failure, right? We see it, we fail all the time. The general public doesn't want to see that. They don't want to see the failures because they're important, critical things at stake here.
Right. In the software development world, we call it, a constant state of being wrong until you finally are right. It's just sort of the natural state of things in this model of development and research and testing. It's but that's okay. It's an okay place to be, even though it's maybe not our most naturally comfortable state that we experience as highly intelligent primates. We kind of want to have things to be like directed and concrete and like this is what it is. But it's once you get past that, and I'm sure we'll explore this more when we talk about what is science later. That state of being wrong is also the same state of being immersed in wonder of possibility. And that's I think kind of where the magic is. And I love that you brought that collaborative team-based movement into focus, because in this story in particular with protein folding, the folding at home scene has been so prevalent in this space for so long that I don't know exactly when folding at home programs started, but it's at least a decade old, I would say.
So let's talk about that for a second, because I'm not familiar with it at all. I am familiar with like SETI's, vast network of looking, for extraterrestrial intelligence, but
oh, my bad. I assume that was a more known thing, but yeah, it's very similar to SETI's program, where you run this application on your computer, especially if you have a nicer graphics card. It can really help. and it just receives orders from the mothership for, here's a protein we have to fold, or here's like a possible way that a protein could fold, I should say. And then your computer just crunches on it and crunches on it and crunches on it, in a much better use of electricity than any Bitcoin or cryptocurrency. And then eventually spits out a result that it either folded or worked in a certain way or did not. And, people are allowed to kind of use that framework to maybe push out some data they need crunching for, whatever experiment they're working on. It's kind of cool how, it's both a way you individually can help out as, somebody who just might have some extra compute at home, but also it's a way to, turn around and offer it as a service to people who require that, which is, pretty huge when you don't maybe work in a place with a huge data center just down the way a little bit,
I do. In fact, know what you're talking about.
I wonder, Jason, like you alluded to, it's a little bit scary going into this world where the average person is able to kind of see the sausage get made, as it were. I wonder if it would actually kind of do the opposite and lead potentially, and this is potentially meaning years down the road with access to this kind of view of science, potentially lead to more trust in the scientific method, because there's the view now that science is like this infallible thing. And I don't think it's a view that's perpetrated by scientists, but it's just kind of out you hear about these scientific discoveries as like a set thing rather than a work in progress, rather than the best answer we have today based on the evidence. And I wonder if finding out how science is a series of failures and tweaking and re-evaluation until you find something that works or you abandon it altogether, if it would almost be good for people to see that happening. The problem is the patience part of things, and maybe I'm too much of an optimist when I think about it that way.
I don't think you're being an optimist at all. I think you're spot on. I mean, I think this is the best way for the general public to understand how science works. But we're at a point now where science literacy is lower than I can ever remember it. And it's not helpful to that process. Because we have people screaming from both sides, right? Either, science is infallible on the one hand, or the scientists are dirty and they're only in it for themselves on the other hand. And so the middle ground is totally lost. Right now, we've got an issue where we don't have a lot of trust in science because we don't know enough about scientists. At least that's my opinion. And so I'm hoping that maybe we can tackle some of that through this podcast. Get to know some of the people doing really cool cutting edge research. They're not so scary. Or if they are scary, right? I mean, let's try to soften their edge a little bit, right?
Well, speaking of soft edges, let's go for the hard edge, and in fact, the barely comprehensible hardest edge that I can possibly throw at you. What am I talking about? Time crystals. You guessed it. We're talking about time crystals. Okay, this one blows my mind. So, to understand time crystals, you kind of have to understand quantum computing, which I regret to inform you is kind of an oxymoron for a human being. However, we're going to put this in the most layman of layman's terms that we possibly can in order to get us to why time crystals are so cool. Okay, regular computing, soon to be legacy computing, which is mind-blowing, basically everything that you see, every action, every calculation that your computer makes eventually boils down to binary. That is to say, a transistor is either open or closed. The switch is on or it is off. With a whole lot of complicated stuff in between that we are just glossing over as if it wasn't an entire, area of study, industry, and giant paradigm shifting facet of the last 40 years of human history. But anyway, or 50.
Yeah, let's just gloss over that.
Let's just gloss right over that and understand, for the purposes of getting to time crystals, that the underlying concept of modern computing is that the switch is either open or closed, and you can kind of get down to that level. But imagine for a sec we could design a system where that switch held more than two states. Imagine that it could theoretically be any number of states. Suddenly, you've totally lost the plot, but if you can kind of hang on to that concept for a second, you can understand why the possibilities for the scale and power of that computational device just grow exponentially from what we can do now. If multiple states can be held within that smallest possible unit of action, then crazy things are possible. And that's why people are so excited about the possibility of quantum computers. All of our cryptography, all of our security, all of the deeply complex math that we've created that make up the security of our modern lives, the ways that you can transmit your credit cards and be reasonably secure that nobody is going to be able to intercept them during the transaction, or your internet traffic, the ways that we can guarantee that your browsing is truly private and the data that you're ingesting is truly private. All of that stuff is based around a certain level of ability that computers have. And quantum computing theoretically can come out of the gate and blow all of that away. It would be so easy to break the craziest encryption that you can throw at it, because it can just work in a way that is so much less restricted than what we have today. Okay, but, and this is a very large but, the problem is those systems that you were imagining are so incredibly complex that the timing required to actually utilize those systems is far beyond what we have ever been able to do. It's, even an atomic clock, which we, consider to be one of the most accurate ways to actually tell time, it still has some fudge factor, some fuzziness in its absolute predictability of having an electron at a certain place every single time. And so, what we have today is an as of yet not peer-reviewed situation, but we're just going to go right to the cool stuff now. A team working under Google has claimed that they have invented a process to create time crystals.
I want to clarify a little bit here, because it's a team working at Stanford.
Oh, thank you.
With Google quantum computing, right? And so it's not Google that's pushing this. It's actually academic research that's pushing this first. Not that Google's not important, but I didn't want this to come off sounding like this was, being generated by a company, right?
Yeah,
this is
it's not just some crazy guys in Southern California.
Right, exactly. This is actually happening in Northern California. It's crazy people in Northern California who come up with these really great ideas,
Far
right?
crazier people in Northern California.
That's right.
Yeah, that's
right.
important. That's important. These researchers have invented a process to create time crystals. And now that we are here, I'm just going to wait. I'm just going to hold on to this a little bit longer because time crystals are just so cool to say.
So I want to be clear. When I read time crystals, I thought for sure this was a mashup of like 1980s fantasy movies, right? But it turns out it was actually a fantasy of Richard Feynman's that he published in the early 80s. So what are time crystals? You keep saying time crystals.
Everybody in the audience is just like, please tell us what time crystals are.
It's
oh my
that
God.
mashup we've always wanted, the Dark Crystal and Time Cop.
So I was thinking Time Bandits, but Time Cop, perfectly acceptable.
Time crystals are a lattice structure, a molecule with a lattice structure that shifts from one lattice structure to another and back again at a specified interval. If that sounds like science fiction, you're right. It up until now, it has been completely outside the realm of possibility. And honestly, I'd be lying to you if I told you that I knew how they do this.
Oh, that's a really good point, right? And I mean, I think that they're still trying to figure out how this is actually working. But what's interesting is that these time crystals represent a new phase of matter, right? They're not a solid, they're not a gas, they're not a liquid, they're not a plasma. They're a time crystal. And the important thing here is that they're changing between lattice structures at regular intervals without any energy.
Right.
This is what is cool. It's a self-sustaining, actual perpetual motion machine.
Right. That's important, especially when you come down to actually thinking about tackling the fabrication of a quantum computer, because this is something that you can stick in, and again, assuming it's all real and works, and we're actually going to be able to mass produce this stuff, which is a whole big assumption on its own.
I mean, yeah. Let's point out that still this is a preprint this has not been peer reviewed yet,
Right.
And so we may not even get to the this paper is accepted stage.
Right. There's a lot of hurdles to clear. But if you get to the point where you're actually thinking about making enough of this stuff to getting them into devices, it solves this core problem that quantum computers have of needing something that exists without a power source, without needing to be resupplied, without needing to be monitored or kept up on, that will allow for the calculations sensitivity, the timing of these calculations it actually makes that possible. So if, and I can't say if enough, and we'll talk about why during, I think, the what is science phase, why this is such a difficult thing to report on, because it is so darn early. But it's,
yes, absolutely.
But it's the type of headline that you only get to see when you live in an era like now, where it still, at least to me, feels like we're just starting to be able to see the future over the horizon, And this year in particular, we talked about the response to coronavirus earlier and the production of these vaccines and the speed at which they've rolled out. It can be so easy to forget and get bogged down in so much of the negativity and bad news that exists, because boy howdy, there sure is plenty of it. But I really liked these stories because for me they represent the paths for me personally to have hope and to remember that we are very fortunate to live when we live and get to see the advancements that we do. And there's plenty of mind-blowing to be done along the way in our own short lifetimes.
I want to talk about that for a second, because you've said it now twice within the last 30 seconds. And when you say it, I see that the same words coming out of my mouth, right? We live in such an awesome time for science. But I have this feeling that throughout history, scientists have always felt that way, right?
That's probably true.
We are at such a cool time in science, right? And so I'm thinking about this book in particular that I've been reading lately called The Butchering Art by Lindsay Fitzharris. It is about the life of Joseph Lister, who really was at the forefront of Victorian-era medicine and our understanding of how to use microscopy to diagnose disease. His father was actually responsible for inventing the actual medical uses for a compound microscope, making it less of a rich person's toy and more of an actual tool for science. And so Joseph Lister took his father's idea and really brought it into medicine. And the reason I'm thinking about this is that earlier this week I had a kitchen knife accident. I pride myself, I've been a gross anatomist for 20 years. I have never cut myself in the laboratory with a scalpel, but I definitely required 7 stitches in my finger from a kitchen knife this week. The whole time I was sitting there, I was thinking to myself, if I lived in Victorian era London, I would die from this. And Joseph Lister had that same thinking that you, Chris, have said multiple times, right? What a cool time to be living for science. We are on the doorstep of what's next, right? What's going to be next? And while I love the enthusiasm for now, I can't help but think that like we've always had that enthusiasm. It's just that now the general public can see it a little bit differently because, again, it's a lot more out there and in your face than it has been for, the last 150 years. Mm-hmm.
I'll also play the devil's advocate and talk about a contemporary of Lister's, sort of, in Semmelweis, where with the wonder and hope for the future, you also have the Semmelweis reflex, which, we've all gotten really into Semmelweis about a year ago when we're like, oh, wash your hands. Without going into too much detail, he's the guy that's like, wash your hands. If you want to know more about Semmelweis, you can listen to a past episode of the Science Night podcast where we talked about him and miasma theory.
I love how you just plugged your podcast on your podcast. I love it.
Always be plugging, right? But basically the Semmelweis reflex is that when you have a new idea, there are a nearly infinite amount of people to slap that idea down, and how dare you have this new idea. I think that the reporting of the time crystal story specifically is too early to have had enough opportunity for people to slap that down, but I am looking through the comments of one of the articles that you linked, and there's a little bit of reflexing happening.
Right. I think that's actually a really important point, James, and that's that scientific consensus is a really powerful thing, but the way that the public uses the term consensus is fundamentally different than the way scientists see consensus. Mm-hmm. When you talk about climate change, for example, there's that common statistic, like 98% of or 96% of climate scientists agree that humans are causing climate change because of greenhouse gases and so on and so forth, right? Burning of fossil fuels. But that's not actually what consensus mean. What they mean by that is not that a certain proportion of the scientists agree with this idea. It's that that proportion of the science published through the peer review process support that conclusion, right? So it might be 98% of scientists. That is incidental to the fact that it's 98% of the science that's published, right? Mm-hmm. There's 2% that suggest that perhaps maybe that's not the case. But when you dig a little bit deeper, that's the stuff that gets smacked down, mm-hmm. right? Mm-hmm. And it's not because scientists don't agree with the assessment out of some sort of, deep-rooted belief. It's that the data don't support the conclusion. Mm-hmm. And so they smack it down, right? I think that's something that we don't talk about enough. We don't talk about the peer review process. We don't talk about what consensus means. And this is why we get in so much trouble with the general public when science changes. I mean, how many of us have seen that, 1 week coffee is good for your heart and the next week it's horrible for your heart, right? It's just because a new study comes out, and one single study is not going to overturn a paradigm ever. It's not going to form a paradigm either. It's that consensus of the published data that form a paradigm, and then a consensus of data that would support overturning that paradigm are required in order to overturn that paradigm.
And far too often that evolving understanding and that capacity for widening understanding is used as a cudgel and used as a weapon or a means to minimize or ignore something that really should be talked about and should be entered into the public consciousness. And your example of climate change is a really good one, because as our understanding of what was happening evolved over time, originally scientists were saying like, hey guys, I think something's wrong here. I think we're heading toward an ice age. And, then time went on and they said, guys, I still think something is wrong here. I think things are getting hot though. And that delta just blew some people's minds to the point where they couldn't handle it. They said, you said it was going to be an ice age and now you're saying it's going to be hot. And then what is it? My goodness, what is it? And it's like, it's an evolving understanding of something that's extremely complex. Maybe you should listen more to the thing where they're saying, guys, I think we have a problem here, and less to the thing where, you don't understand the why and so you attack. Just a personal opinion.
No, I'm with you. It's my personal opinion too. I appreciate you for sharing it because it's like you got right in my head. I actually think this whole discussion about climate change is is going to need its own
series. We're tickling
of
something
episodes,
that
right?
we don't have the minutes for right now.
We have a clear sort of mandate to do it now. So let's do it. Let's make that happen.
Science Night will have a climate change episode, and maybe even more than one.
I mean, Science Night, dare I say it, is even undergoing its own climate change as we speak.
There we go. And it's heating up. It's getting hot, folks. We'll be right back, but first, a quick commercial break.
Hi, I'm Matt. And I'm Phil. And together, we host the History's B-Side podcast.
You know, history is full of amazing stories and memorable people.
But we don't care about them.
Every week, we break down history's biggest stories and the forgotten people who made them happen.
We're not historians. We're just two guys who enjoy a great story and plenty of laughs.
Find us on Apple Podcasts, Spotify, Amazon Music, and more.
Or follow at History's B-Side on Facebook, Twitter, Instagram, and YouTube.
This is History's B-Side.
So we've been talking a lot about different aspects of science and how the academic system works, how the lab system works. But, you know, in coming up with segments for this show, one of my favorite colleagues asked me a very important question.
What is science? I love science.
So that was my dear daughter asking me the question, what is science? And it was not a question that I had an immediate answer to. So what I did with my immense power and persuasion was went to people who might have a better answer than me, actual scientists, and I asked them the question, what is science?
What is science? That's a great question that no one's asked me. Curiosity.
Science is how we, as a society, create the solutions that get us from point A to point B. And when done right, it's democratic, so that everyone has a voice in creating those solutions.
Science is a way of thinking. It's a way of learning about the world. It's a way of asking questions and getting reliable and repeatable answers. It's important that the evidence that science produces is treated honestly, and that's what science tries to promote, is the sort of honest learning from the results of experiments.
Science is one of the ways that we meet one another. Science gives us all a common language that we can use to understand our lives, our place in it, and how we can take care of our planet. Science is the Rosetta Stone to unlocking the great questions of life.
Science is our way of observing and understanding the natural world with, at least in theory, probably as close to the Platonic ideal of objectivity as our species can manage. It's the systematic pursuit of knowledge. It's constantly being rewritten and tested so we can better understand the underpinnings of ourselves and the universe around us.
Science is the production of convincing knowledge in modern society. Production because it's active, not passive. Convincing because there's always an imaginary, open-minded interlocutor present. Knowledge, not feelings. And it's based on cultural assumptions derived from 17th century European philosophy. Science is the production of convincing knowledge in modern society.
Science, in my opinion, is a way of looking at the world and understanding it. It's the curiosity to find out more and the methodology to help us find out more. And I think it's mostly driven by the creativity and the wonder we have for what is happening around us in the world that drives science.
So those are the answers that we got from a select group of scientists.
I love it. Absolutely love it. Because it encapsulates pretty much everything that I've thought at one point, but puts a much finer point on it than I ever did. You know, to me, Science is a process. And all of those answers really sort of get at that singularity, right? It's not anything finite. It is constantly changing. It's self-correcting and iterative. And because of that, it is best described as a process for understanding the natural world. And I say that actually to differentiate it from the supernatural world, which is the realm of religion, which attempts to, explain phenomena through the supernatural world. That science can't do that. And so there's really not a conflict, in my opinion, between science and religion because of that. They answer questions about different realms altogether. And so I really love all of these answers.
Yeah, I do too. And I can't be a huge Sixers fan without saying we have to trust the process.
Or I'm a Royals fan, so I get it. I've been trusting the process since 1985. It worked once. But it worked. It worked, baby.
But what I really loved and appreciated in hearing that is that there is room for creativity and curiosity and wonder. I would say that is paramount in the thought process of what is science. You're not going to be a scientist if you're not asking a question of how does this do this thing? I've only met the scientists I've met, but you get them talking about their work in a non-formal setting, and that's where they really come alive. Now, I will leave room for there being a lot of work to do when they are communicating their work in what they could think of as a formal setting, and not turning that off when they get off the formal pulpit, as it were. You do have the scientists that they kind of have the one delivery, and that's something where we can work to, but it's not that there's a lack of creativity or a lack of curiosity or a lack of excitement.
I just wanted to sort of point out that you were referring to scientists communicating with other scientists, James, and most scientists are effective at doing that. They have to be, or they are ineffective as a scientist, right? I mean, it's hard to form collaborations. It's hard to get grant money. If you can't communicate what you're doing to people who know a little bit about what you're doing. But where the rubber meets the road is the federal taxpayers, right? Because that's ultimately what's funding most of the science. And so I couldn't agree with you more. The moment you get people to start talking about their work to non-specialists, you start to learn that they're people. And they're people in a way that you didn't actually expect them to be people. We spend a lot of time here in my job in academia trying to train scientists to become better at communicating their science to people who don't know a thing about what they do. And a lot of that starts with, trying to form a connection to an audience. And how do you do that? You make yourself relatable. The best advice I ever got when I was finishing up my PhD and looking for a permanent job, whether it's a postdoctoral position or I guess that wouldn't be fully permanent, but more permanent than I had at that point in my career, or a professor position, was that I should put myself in my science. And I got that information passed down from generations earlier of graduate students, right? That's the best way to land a job, is to put yourself in your science. What does that mean? I thought that just meant putting a picture of me doing field work in my slides, right? And it turns out that actually there might be something to that, because if you put a picture of yourself doing field work in your slide deck, you now have an opportunity to talk about what you did in a way that is more conversational than, it's like showing vacation pictures. Not to suggest that field work is a vacation, although I did do field work in Costa Rica at an ecotourism resort with marble showers. So it wasn't exactly the same as going to Madagascar, for example, or, excavating fossils in Montana, right? Or in the Badlands. Maybe it was a vacation. But the point is, putting a picture of that into a slide deck means now I have an opportunity during a talk to talk about something that's not specific to the science, but specific to the process of that science. Again, this is how we collected these data. This is what we did, right? And I think it's important to remind folks that scientists have those kinds of stories, right? I mean, some of the best stories I think I've ever heard are stories about someone's truck breaking down out in the field and the ingenuity that is required to get them out of a sticky situation. It's always fun to listen to, mostly because I wasn't part of that story and I wasn't the one panicking. And we know that everything turned out okay because they're with us, right? It could always be worse, but when you can hear those stories, right, it makes you more empathetic to sort of what they were experiencing, and it actually makes them more relatable as people.
One thing all of those offerings that people sent in made me think about was something it doesn't. This part doesn't come from science, but I'll bring it back around. I promise. One of the most formative books I ever read was Tribe by Sebastian Junger, and he talks about a lot of stuff in that book. But one of the things that I really, really liked and appreciated was this idea that one of humanity's superpowers is that when we encounter a problem we cannot individually solve, we create imaginary structures that can. When we can't get enough food to everyone around us individually, when we can't farm enough by our own hands to solve that problem, we create markets to exchange them. And, in reality, it's just a big place where people are, but there's this concept we attach to it, and so we solve the problem through our collective imaginationing of that market. Government's the same way. Markets get really big, so we decide to have something that exists to work within that framework to help control it and regulate it. So we imagine this thing called a government, which places a structure that's imaginary around this other imaginary structures all the way down. And so when they talk about the process, that iteration, when we can't understand the universe and ourselves and everything around us and in it, we create these structures. We imagine the ways that you would be able to deduce how the universe would work. What are the steps one would go through to prove how the universe works? And that's science. This collective operation of imagining a solution to a problem and then testing it to see. And I love that more and more we're talking about that as a shared experience. Going back to that thing that makes humanity super, that thing that we're really, really good at, that collective imagining. And to hear that reinforced in everyone's ideas of what science is and how it should work is well, it's makes me feel like we are actually going in the right direction.
Yeah, so maybe back to the point about team-based science being sort of the forefront, right? Maybe that's what sets us apart now from the time of, say, Joseph Lister, right? And that we have team-based approaches now that are built in and baked into the system in a way that we never had before. It used to be a single lab would get a grant, and the NSF or the NIH would fund that lab over and over and over again to run a research program. Well, it's very hard to get a grant as a single laboratory anymore, because the kinds of questions that are possible to answer with only one lab are few and far between, right? The kinds of questions that we want to answer, that we need answered, that the ones that federal taxpayers are going to reap the most benefit from understanding, or at least application of the understanding of those things, are all rooted in team-based approaches because they are so diverse. And the techniques that are required to answer those questions are widespread and not possible to do with a single laboratory alone.
And I think also another good point is those teams are becoming not just like inter-university, but they're becoming interdisciplinary
Absolutely.
as well. One of the things I love to kind of facilitate in my professional life, but also just see happen in my personal life, is something called de-siloing. And that is basically when you get into the academy, when you get into a university, especially a research institution, there are these artificial walls that are keeping not just the humanities and the sciences and the arts separate, but also keeping the anthropologists away from the biologists and the epidemiologists away from the other scientists. I'm running out of scientists off the top of my head. And interdisciplinary approaches are really interesting because they're kind of bringing this entire multiple viewpoints into the primary research. And it's extremely interesting, and maybe we should talk about really quickly the difference between basic research and applied research. Basic research being like the big questions, the how, the why. And then the applied research is using that to do something.
I think you're kind of really hinting at the fundamental difference between what the National Science Foundation would fund versus what the National Institutes of Health would fund, right? So the NSF, National Science Foundation, would fund things like basic discovery of a biochemical compound, right? How does a protein fold? That would be, an NSF type research program. But how does a protein fold? And how is that going to help us cure X disease? That's an NIH approach, right? And so NIH is focused on health-related, solutions to health-related problems that have come out of basic discovery, basic science. So it is a lot more applied in that regard. Although, again, the NIH still does fund basic discovery. It's just that it doesn't fund basic discovery alone. It has to be in combination with a treatment potential for a disease or a new approach to treating a disease.
Mm-hmm. And when you're looking at, bringing an interdisciplinary, multi-team approach to basic discovery, you basically have a lot more eyes with a lot more different experiences looking at these big, hard to answer questions. And so if you've ever asked yourself, like, why does it seem like this thing has just kind of sped up all of a sudden? Sometimes it's because this one person had this profound idea and it turned out to be accurate. A lot of times it's just because the amount of people that were thinking about and working on this project and sharing their information amongst each other got to the point where they saw something new in the data set, and that lit a fuse that led to this thing.
I mean, it's fun to see those kinds of ideas come to fruition, especially after a long stall in advancements, right? But it's true. Science does work in fits and starts, right? It really does work in sort of a punctuated fashion where you have really rapid changes and then a long period of not much change. But then something will happen, right? Like a new computing technology, for example, right? Quantum computing is now allowing creations of time crystals that were only theoretical in the early 80s, but now may or may not, depending on whether or not that makes it through peer review and can be replicated and so on and so forth, may be a regular part of our understanding of physics now. That's fascinating and really cool. But it took a long time to get there, right? 1982 was a long time ago.
It's true that it does, like, from our small, organic human perspective, it feels like it's taken, forever. But at the same time, it's really just a blink of an eye. The changes humans are making now, it's hard to live through because, especially when you're a geek, you just already want to be in Star Trek. At least I do, But at the same time, when we look back and, just down the street from me, they 100 years ago were probably more like 150 years ago, they were cranking out farm machinery parts in a massively modern way that had never really been done at that scale, and people were amazed at the process and the how prolific they were with the amount of output of product. And you can see the effects of that infrastructure everywhere and of those processes, but it's all just gone and completely irrelevant now. Though we couldn't have what we had without it. We couldn't have today without that. From everybody who has been on this hill from that point until now, it's been lifetimes. But in reality, it's just a couple generations ago.
Totally agree. Just this morning, my 10-year-old asked me how old I was when we got our first flat screen TV, and he was crushed to learn it was only a couple years before he was born. What do you mean? You had one of those weird, like, curved screens on your TV?
Right.
Yes, I did. It was also like a huge console, and it like weighed 300 pounds, and like it was awful.
And by the way, kid, we used to fix them too.
That's right.
You know, the most profound thing I like to point out to people when they're talking about it taking forever to make that new discovery is the amount of time between the first flight of the Wright brothers, 1903, and the moon landing was 66 years. That is very likely there are people that were born and lived through this entire process of figuring out how to have sustained mechanical flight to going to a different place and then coming back. I mean, that is pretty incredible that it didn't take 5,000 years. There is thousands of things that are happening behind the scenes, and we just kind of find out about them when they're towards the end. And maybe that is tying back to my original thought of if people are able to see the process, maybe they will be able to trust it a little bit more. Maybe it'll make them excited to learn more about it, and that can help with the scientific literacy as well.
And if there are thousands of things happening behind the scenes, then we will have so much material for this podcast. My goodness.
That is so true.
I would say that it's interesting that we've gone 2.7-ish million years from stone tools to space flight, right?
Sure.
I mean, but it was only 66 years, as you said, right?
Right.
From first sustained flight, mechanical flight, to space, right? It was still 2.7 million years to get from stone tools to that.
Well, and like a different thing too, right? That's the other part is in that 2.7, like there were other things, not Homo sapiens, that were figuring that out too. Like we kind of lumped on to work that was done before Homo sapiens even got on the scene.
That's true.
In that aspect. So if you want to really talk about this being a process, like this is a process spanning other animals.
I'm reminded of that famous quote from Og the Caveman when he said, "If I have seen further, it was by standing on top of Thad the Neanderthal."
Yep, for sure. Absolutely. Yeah, I mean, talk about team-based science, right?
Right.
When we're talking about crossing species lines, even more impressive.
Hey everyone, it is James from the future, and I am dropping in to talk to you about the River Power Podcast Mill. This podcast, like so many others, is a member of a podcast collective where we come together to bring you great entertainment. If you'd like to know more about the shows on the River Power Podcast Mill, or if you're interested in getting into podcast, you have a great idea, you're excited to get started, head over to riverpower.xyz. Our last segment in our relaunch episode, I wanted to bring you something a little different and really special. Our friends over at the History's B-Side podcast brought me on to talk about one of my favorite people in history. His name is Alfred Wallace, and he was really important in the discovery and implementation of evolution by natural selection, also known as Darwinism. So right now, I'm going to play you the first 20 or so minutes of that podcast. If you want to hear the rest, and you're going to want to hear the rest, go over to their feed. That is History's B-Sides. Start with this one because we got to have that shameless self-promotion, and then listen to everything else they have going on. So without further ado, here is the beginning of my episode from the History's B-Side podcast, Alfred Wallace, the stepfather of evolution.
Today's B-Sider is the stepfather of evolution.
So today we're really fortunate to be joined by our friend James Reed. He's going to be guest hosting this episode. He was actually got in contact with us to suggest today's topic, and he seemed so passionate and knowledgeable about it that we just decided to invite him on and have a guest host here and mix things up. So James is, just to give you a little background on him before he starts us off, he's originally from rural Pennsylvania, now living in just as rural Vermont. He's currently an anatomy lab director who's involved in scientific outreach, and he's joining us from the Science Night podcast, which you can find at SCINIGHT.com. Welcome, James.
Thank you so much. I'm really happy to be here. I'm excited to talk about the stepfather of evolution. But before we get into that, we got to talk a little bit about evolution. I can't just be a bad science communicator and not actually tell you what evolution is, because some people have different ideas about that, what that means. And most of this episode is going to talk about evolution by natural selection. But I think it's a good idea to go over what the prevailing thoughts were during the Victorian era, when people like Charles Darwin and the person we're going to talk about, Alfred Wallace, were coming up with their ideas. The first thing we have to talk about is creationism. And that is a list so long that we could not possibly talk about everybody on it, so I'm not even going to try. But there are two main people during the Victorian era that bear mentioning. And I have very strong opinions about both of them that I will try to keep hidden. So the first person is Georges Cuvier. He's a nice Frenchman with a nice French name. And he's most well remembered for his work in the field of vertebrate paleontology, which is the study of extinct vertebrates. A vertebrate is anything with a backbone. And then he's also well known for stratigraphy, which is the idea that different layers of the Earth represent different times. And one of his pet projects was comparative anatomy, which was using the anatomy of different living specimens to kind of inform how development may work in them. And we use that today, too, all the time.
It's really good that you're explaining all of these and define them simply for us, because we're kind of dumb anyway, but especially we're a history podcast, kind of a science angle on it is really useful to us.
You said stratigraphy, and I was like, that's how that's pronounced.
I said, did he pronounce that right? I've never heard that word.
Yeah. It's all about how you say it, not what you say. So, kind of the infamous thing about Mr. Cuvier, probably doctor, why not? Is he was really well known for coming down hard on people who even came up with something close to evolution, or what he would have called transmutation, which is kind of a cooler name. I guess it's less Pokemon based at that point. And that's why the idea never really took off. He was like the giant of what would be called biology. It was natural history, I guess naturalism at the time. And he just kind of was a voice so large that no one dare go against him.
So it seems kind of wild that his criticisms were so harsh as to discourage all the other researchers. I mean, I know it was a different time where, even Newtonian physics or evolution or things that we today think of as kind of commonplace scientific knowledge were still budding. But can you summarize his main criticisms that he was so harsh about espousing?
Yeah. So they're not without a little bit of merit. So he worked with fossils, which were kind of a new thing at the time. We as a scientific community had just realized what they were. We thought they were anything from chunks of rocks to dragon bones in some parts of the world. But he argued that since the fossils he was finding just kind of appeared and then disappeared over time, that it was impossible for something to change into something else on its own. And basically he was bringing his biological hypotheses more into line with biblical creationism at that time. So he felt that only the hand of a creator could change a species.
So his objections to evolution or transmutation, or whatever he called it, were just based on religious objection. Did he have any kind of counter scientific evidence to justify his argument?
Yeah, that's a really good question, because he did feel like he was being very scientific about what he's doing, because he's using the research that he is conducting. What he's doing poorly as a scientist is looking at the evidence and using that to draw his conclusion. So basically, he's coming in with a conclusion that the hand of a creator is necessary for a species to change, and he's not allowing evidence, which was kind of scant at the time, to sway his opinion either way. So instead of going into these scientific salons with an open heart and an open mind, he was being very French about it.
Very French.
Yeah. And the other person, they used to call him England's Cuvier, and he hated that, is Richard Owen. He wanted to be more well known as England's Owen, but that just wasn't going to happen. So like Cuvier, he was a paleontologist. He was really well known for being able to interpret fossil skeletons, specifically birds, lizards, and fish. And he's the person who actually came up with the word dinosaur, which is cool.
What does it mean to interpret a skeleton or a fossil?
Right. So he was really good at looking at an arm bone, a fossil arm bone, because I guess take a step back. Fossils don't look as pretty as they do when you go to like the Natural History Museum in New York or the Field Museum in Chicago. So there's a lot of deciding what is fossilized bone, what is just rock, for starters. And then you have to be able to look at an extinct species and interpret what the parts of the body are doing. And to do that, you have to have a good idea of living species. And that's what Richard Owen was really good at. So again, bringing comparative anatomy into his work with paleontology. And he was less of a strict biblical, like Judeo-Christian biblical creationist. He was more of somebody who thought of the world in Platonic ideals or like Platonic forms. Unlike Cuvier, who did die, we'll give him a little bit of credit. He did die before Charles Darwin came out with his work. He also may be the reason that Charles Darwin waited quite a bit to come out with his work. But Richard Owen did come to accept the larger pieces of evidence that Charles Darwin was coming out with, eventually, kicking and screaming, but he did get there.
I'm familiar-ish with the Platonic ideals thing, but I'm a little fuzzy on. It's been like 6 years since I took an intro to philosophy course. But how did he suggest that the biological development was following the forms? Like, was he suggesting that species themselves were striving over time to reach those forms, or that they were created from those forms?
Yeah, it's actually. Instead of striving towards, it's the opposite. He believed that there was like these set archetypes, and he came up with the word archetype to decide this. So everything fits into these several archetypes. Specifically, he believed that all vertebrates came from the same vertebrate thing. And that's not unlike what we would talk about with natural selection. But where we differ is that he thought from that archetypal point, all of the changes were done by a god, or, well, he would not have actually used the word God. He would have used like universal energy or something like that. He felt that the energy within the species was this like universal form that was driving something forward. So it wasn't it wasn't that the species themselves were striving towards something. It was that the universe was striving towards something, which is really out there. So the fact that you're able to get to that point, but not being like, well, over time things change, is a little remarkable. So, like I said, I got really strong opinions on Cuvier and Owen. They were jerks. They were not nice guys, but they were brilliant in their own fields. The problem with science during the Victorian era is that these natural philosophers or natural scientists were kind of responsible for everything under the sun. So they were expected to know everything there was to know about geology, biology, anatomy, these things that are separate fields. They were supposedly experts in all of them. And that comes through where you have people who know a lot about very specific things, but then they say wild stuff about other things. Not unlike Alfred Wallace, which we'll get into a little bit later. But the next thing I want to talk about is one of my favorite, pet theories. It's obviously not something that is a credible hypothesis anymore. The evidence has moved us away from it, but it's kind of what you would expect the people that make Pokemon to have used as their model, and that's Lamarckian inheritance. So this is another good Frenchman, Jean-Baptiste Lamarck. He thought that physical characteristics of the parents, and this is not the genes, because they knew nothing about genetics at this point. So he thought the physical characteristics would be inherited by their offspring. And this would be like you getting braces so that your children would have very beautiful, photo shoot ready, straight teeth. And he loved using giraffes as his model for this hypothesis. And he thought that the kind of precursor species of what we would think of as a giraffe had a really short neck, and the act of stretching up to get leaves was what led to them having a long neck. This assumes something called orthogenesis, and that means that the species is driving towards a more complex form. And a good way to think about this is the March of Progress image, which you can see on coffee cups and mouse pads and t-shirts. And it is almost always a monkey turning into a chimpanzee, turning into a caveman, turning into occasionally Chuck Norris or whatever funny thing you want to add there. It is not scientifically accurate. It's usually a little bit racist too. But that's what we're thinking of there. Not to think that everything about Lamarckian inheritance is super problematic or anything.
I mean, if this was true, orthodontists everywhere would be losing their money.
Right. Yeah, we would have figured this out in the first time braces were invented. Like, get it going and get it done.
Plastic surgery, there'd be no future market for it.
If this were true, I'd be 6'8", because I've spent the last 10 years trying to make myself taller around women.
How's that working out for you?
It's not. I'm still 5'6". So
yeah,
Lamarck was wrong. I haven't gained an inch.
Exactly. And this brings us to the actual thing we're going to talk about, natural selection, or Darwinian evolution. And the best way to think about this is descent with modification. And because we're calling it Darwinian evolution, obviously Charles Darwin came up with this and no one thought about it before him. It's not like you can look at ancient Arabic texts and see somebody like Avicenna say, literally, I think that species come about due to descent with modification. In the language of the time. He wasn't speaking in modern English, although he was pretty smart, so who knows?
If you're telling us that someone else came up with it way before Darwin, we're going to have to now do research for another episode.
Yeah. Well, Avicenna's not necessarily a B-sider. He's pretty well known. Another way, and a more popular way to talk about evolution by natural selection, is survival of the fittest. A lot of people don't think of fittest in a biological sense. They'll think like Arnold Schwarzenegger, Usain Bolt, like able to run fast, lift heavy things, that kind of thing. But what we talk about in biology is fitness, is the ability for things to reproduce. So for an adaptation to move forward, the species has to be able to pass those genes on in whatever way they do. So if a species is seen as unfit, that means that they either die before they're able to reproduce, or they are not able to reproduce successfully. So they have maybe they have a reproductive system that's overly complex and they just do not reproduce at a rate fast enough for the numbers to keep up. And if we want to use Lamarck's giraffe metaphor, giraffes with longer necks were better able to get food by reaching higher than the other things around them. So those slightly longer necked giraffes were able to pass on their genes, and those offspring with longer necks were able to get food and continue going on and on and on until you have what we have now. And a giraffe is definitely a species that you would consider a specialist because it feeds on one thing.
Do you see Lamarck's ideas as detrimental to the proper understanding of Darwin/Wallace's evolution? Because that's kind of what I'm getting as I read it. I feel like some of today's criticisms of evolution seem to almost muddle the Lamarckian concept without seeing the subtle distinction you're talking about.
Sure. Yeah. So not really. Talking about Lamarckian evolution is kind of a nice way to talk about how science actually works. Because you have to remember that science isn't a thing. There isn't a known quantity of science available to us. It's just
I would like to buy one science.
Exactly. I'd love to sell it to you. But think of science as a tool that we can use to explain the world around us. Lamarck, he came up with an idea based on what he had to look at the time. Darwin was a follower of Lamarckism, and he was able to use the information that he then gathered to build on that hypothesis.
Okay.
Part of the thing that when you talk about the theory of evolution is that people think of theory as we would use it colloquially, not scientifically. So a theory is something that has been proven over and over and over again. It's the most rigorous term that we can give to a scientific hypothesis. Part of the problem is not necessarily that people are dumb. It's that scientists are bad at communicating their work. So
enter Science Night.
Exactly.
Right, that's what I was going to say.
That's
we
right.
Need a podcast
exactly.
To help communicate that.
And what we really need to get better at is kind of meeting people where they are, regardless of how scientifically fluent or what education level they get at. If you are an expert in your field, you should be able to communicate that to a kindergarten class. That's kind of where I'm at. I'm trying to be at the kindergarten level, as a good science communicator.
Mm-hmm.
So speaking of kindergarten level education, I'm coming in here with a dumb question. So we'd use the giraffe analogy. Do giraffes have a significantly longer neck now than they did 200 years ago in Lamarck's time? Or is it a much slower process?
So they do not have a significantly longer neck than they would during Lamarck's time, but they do have a significantly longer neck than they would have had a million years ago. The precursor, last common ancestor to a giraffe and other things that are related to a giraffe would have had a shorter neck. But the thing to remember is that evolution doesn't fix a set of problems, and it doesn't adhere to a strict timeline. It's a response to the environment over generations. So Some animals, like a fruit fly, have a very short lifespan. So they can start to show genetic differences over the course of a few weeks. And that would be in the gene lines, not necessarily able to be distinguished by the naked eye or even by a microscope. But in the genetic lines, you can see differences over a few weeks because they're mating and dying every day. A giraffe. Oh, and because of that, a fruit fly can adapt to the environmental changes really quickly. You can notice that fruit flies just kind of appear when fruit rots. So they're able to kind of adapt to that situation really quickly. A giraffe is, like I said, it's a specialist, and it also has a longer lifespan. So if the acacia trees that they eat in Africa were to die off in the next 2 decades, which is like a real possibility, the giraffe would not be able to respond to that on its own. And that is where you see extinction. Extinction events tend to happen with climate change. Spoilers, it's kind of a big deal in our work. So Charles Darwin is most well known as the father of evolution, or the father of evolution by natural selection. And his work as the naturalist, which was like kind of like the science guy, or like a fancy science guy, because they're usually from the nobility, aboard the HMS Beagle, provided a lot of evidence that led to its widespread acceptance. But as we will see, there were a lot of other people who were starting to have these observations about the natural world, and they all came to a similar conclusion.
Well, you're the fancy science guy on our podcast, so thanks for giving us the brief overview. Why don't we take a quick break, and then we'll get into more of Alfred Wallace's story.
We'll be right back.
That is going to do it for us. My name is James Reed, and if you want to follow me, you can go to my Twitter at James_Reed3.
I am at GR8GOULET. That's the Great Goulet at Twitter. And you can find anything else you want to know about me at ChristopherGoulet.com.
And I'm Jason Organ, and you can follow me on Twitter at OrganJM.
If you want to find out more about any of the topics we covered in this episode, go to SciNight, that's SciNIGHT.com, or you can follow us on Twitter at ScienceNight1. We'll put up any information about upcoming guests, upcoming episodes, and potentially even live streams on those handles. And don't forget to check out our friends over at the History's B-Side podcast. If you really liked that teaser for the Alfred Wallace segment, go check out their feed.
And we are very proud to be members of the River Power Podcast Mill Network. The River Power Network is the gas in our tank, the lift under our wings, the wind in our sails, and the rushing water turning the wheels of gumption that powers this creativity. And we thank all of our fellow podcasts and creators at the River Power Podcast Mill, which you can find at riverpower.xyz.
That is going to do it for this edition of the Science Night podcast. We will be back in 2 weeks. Until then, have a great night. Special thanks to Craig Byron, Jon Marks, Brian Shearer, Ann Burrows, Jen Ma, Steffi Diem, and Ben Valentine for answering the question, what is science? And of course, to Hannah Reed for asking the question. I think this is it. We're just going to put this in unedited. You know, like a 25-minute discussion. We have to at least be to 1,000 subs.
Because we're not trying to get an audience, right? We're trying to scare them away immediately. Yeah?
Right.
Yeah, no.
Yeah. No, then definitely this should be it.
Can you get negative downloads?